right. Hello again. We'll continue with the chapter 5 of the textbook by Shrikant and Ying. This is on scheduling and wireless networks. So what is the difference of a wireless network from the network architecture that we talked about earlier? Basically, the main difference of a wireless network from a wired network is that nodes tend to compete in an environment for a common resource, which is the wireless spectrum. So there is this situation of the signals of everyone being in the air together, and they could interfere with each other. This happens, of course, you may say in an optical cable using Ethernet, there is contention as well, but in wireless this tends to happen more. So the medium access control algorithm is very important, and the medium access can sometimes be solved through random access. Sometimes it can be solved through scheduling. So at the moment, for this chapter, we'll consider the scheduling of wireless transmissions of multiple nodes. Now, let me see if I can get some control on marking this page. So first of all, I will try to see if I can use this marker. Oops. Or maybe a highlighter. I don't think it's going to be working. Let me see. So let's start by defining an SNR for user IJ. So what do we mean by a user? We think about a transmitter and a receiver. Let's call them I and J. The SNR, the signal to noise ratio on link IJ, will be simply given as the following: Hij of t, pj over sigma j squared. Here, sigma j squared is the noise variance for the receiver j. This assumes, of course, additive white Gaussian noise, which is most often the case, most often the assumption in communication theory. Pij is the power used by a transmitter of link IJ. Okay, I'm sorry. Wait. Do you see the screen? Yes. What is Hij of t, do you think?
The channel from the user I to destined J?
Exactly. This is the channel gain. This is the power gain of the channel. And it is a product of many different factors, such as attenuation, fading, shadowing, etc. There are many different effects due to interference and from other sources, and shadowing, attenuation, etc. But a simple model for it is, first of all, a power loss with distance multiplied by a time-varying component, time-varying fading component R of t. Now, the path loss with distance is usually exponential, distance to the power negative alpha, where alpha can vary from usually 2 to 4 depending on the environment. Of course, you know, free space loss goes like dij to the negative 2. Now, given that, so for the rest of the chapter, suppose this is our model. We have been given a channel gain Hij of t. Okay, and with that we can compute SNR, and this SNR is time varying in general, and is of course a function of the power used by the transmitter. Okay, Pij. Now in this chapter we'll adopt three models. The first is when the channel gain is constant. By the way, can you see my cursor as I go over this document?
Yes.
Do you see the cursor here?
Yes.
Okay, good. So when the channel gain is constant, this corresponds to a constant rate in packets per time slot. Okay. Another alternative is, so basically channel gain is constant means there's no change in the channel and we use a constant power level. So we always get the same rates. This is the simplest model. Another model is the rate available to the transmitter comes from a finite set of rates, R1, R2 through to Rk, and the transmitter can pick a rate for every SNR depending on the channel gain and its available power. This is called adaptive coding and modulation. Okay, you may have learned about it in your wireless course if you took a wireless course. The third model we'll use is that the channel gain comes from a finite set of channel states. So channel is one of a finite number of states. Each has a steady state probability. So the probability of the mth state is pi sub m. This is the fading channel model. This is actually quite similar to the previous model, except in this one on the left, we are using the power to control our rate. In the one on the right, the channel state will be beyond our control, and then we're given a channel state, and essentially we have to adapt by designing our scheduling policy. You know how much which user to schedule in what channel state, etc. Okay. Now we will say for the rest of this chapter, for simplicity, we assume point-to-point transmission. The transmitter can transmit to a single receiver at a time. And if there are multiple transmissions at the same time, this will be considered interference. Of course, those of you who have taken advanced communication courses know that it is possible to design a multiple access channel, use a multi-user code where multiple users can receive information at the same time. But this is going to be ignored by the rest of this discussion. In fact, in real life too, this is ignored most of the time, and most communication physical layer architectures still use single user coding. Okay, so now when there are multiple transmissions, okay, that constitute interference on each other, it can be shown if we are using Gaussian codebooks with Gaussian interference, that is, that you can, under some conditions, treat the other user's signal as noise. And then we can define an SINR, a signal to interference plus noise ratio, which is basically the ratio of the received signal power to the received noise plus interference power. So let's see this example of two nodes, node 1 and node 3 transmitting to their respective intended receivers, node 2 and node 4. So node 1 intends to communicate to node 2 using power P1, and node 3 intends to communicate to node 4. Okay, now the channel state from node 1 to node 2 is H12 of T. So the SINR at node 2 is P1 times H12 of T, which is the power received at node 2, divided by the noise variance N2 at the node 2 receiver plus P3H32. So this is the power received from node 3 by node 2, which will be acting as interference. Okay, so you can, from basically, we know from information theory that if we treat interference as noise and everything is Gaussian, etc., the rates achieved are R12 and R34 in this form, 1/2 log 1 plus SR, basically. So we are able to achieve, the two nodes are able to achieve these two rates, R12 of T and R34 of T. Okay, so this is one model that we'll use. Let's see. This suboptimal approach of encoding leads to vector of channel gains R12, R34. These live inside a finite, M could be a finite set of states if our possible channel gains and power levels form a finite set. Let's take a special case of orthogonal transmission where we don't let the two users to transmit at the same time. So either node 2 transmits, that is link 1, 2 is activated, then the rate vectors are 1, 0. Rate vector is 1, 0. Or link 3, 4 is activated, rate vector is 0, 1. Or both transmitters are silent, 0, 0. Is that okay? So with orthogonal transmission, we have three possible rate vectors. Okay, the question is which rate vector to choose when? This is the scheduling problem. Okay, we can solve this problem in a centralized way or in an ad hoc way. Centralized way means there's a centralized decision maker or scheduler that decides which rate vector to choose at any given time. Okay, the ad hoc way, each user decides on its own. So let's talk about the essentially. So how to do this? Okay, we could do this in a channel-aware way. We could make this decision in a way that we're aware of the channel states, or by ignoring the channel states, agnostic of the channel states. So let's talk about channel-aware scheduling. Suppose each channel is on or off equiprobably. Okay, so there's a flow. So let's consider this example. There's a base station, and in the downlink, we are trying to schedule flows to two mobiles. Okay, this is the simplest possible downlink scenario. But once we understand that, of course, it would be possible to generalize it to a more realistic scenario. All right. So now in this downlink, the centralized scheduler is going to decide which user to send data to at any given time. It can do it in a channel unaware way or channel aware way. The purpose of this section is to show how much more we can achieve by channel aware scheduling. Because channel unaware scheduling would be the usual, second generation cellular communication, the original GSM system in Europe, for example. There's not much adaptation based on channel or user traffic criteria, etc. But now, in the age of LTE, 5G, and toward sixth generation cellular networks, everything has to be adapted to the channel state and to the traffic of the users, as well as other things, other areas. So let's see. Excuse me. So in channel unaware scheduling, the base station will select a mobile I with probability alpha I and transmit a packet. The rate allocated to user I is going to be alpha I times the probability that the channel of user I is on. Because if we allocate the channel to user I, but it happens to be off, the user won't be able to get any service. So anyway, the channel is on with probability 1/2. So the average rate is lambda alpha I over 2. By symmetry, the rate achieved by the second user is, both users basically is alpha 1 over 2 and alpha 2 over 2. And since the fractions alpha 1 and alpha 2 have to add to 1 at most, this is the achievable rate region by channel unaware scheduling. R1 and R2 take values inside this triangle. 1/2, 1/2. Okay. How about if we applied a scheduling that is aware of the channel, a smarter scheduling algorithm? Here, the base station uses the knowledge of the channel. When only one channel is on, of course, schedule that channel. When both channels are on, schedule user I with probability alpha I, for example, in general. So what is the rate received by user I? R sub I is 1/4, basically with probability 1 over 4, only user I's channel is on. In that case, it gets a rate, right? It gets to use the channel by itself. Why is it 1 over 4? Because the channels are on or off independently of each other. So the probability that they're both on is 1/2 times 1/2, which is 1 over 4. And with probability 1 over 4, both channels are on, and user I's channel is selected with probability alpha I. User I is selected for transmission with probability alpha I. So the rate, then, average rate, is 1 plus alpha I over 4. Is that clear? So then what is the region of rates achievable by channel-aware scheduling? So the service rates are within 1 plus alpha 1 over 4 and 1 plus alpha 2 over 4, such that alpha 1 plus alpha 2 add to 1. Okay, what kind of region is that? That gives us this pentagon, whose border is shown by a dashed line. Okay, so for example, the point 1 over 4, 1/2 is achievable by this policy, whereas it was not achievable by channel unaware scheduling. So the achievable rate region of channel unaware scheduling is strictly within the achievable region of aware scheduling. We can later on prove that, in fact, this pentagon is also the capacity region of this network model. Okay, so before that, let's talk a little bit about max rate for the cellular downlink. Do you have any questions so far? All right, so let's talk about max rate. Now, suppose in general there are M channel states and the base station can select one mobile at a time. Okay, let C sub M be the rate vector when the channel is in state M. C sub Mi is the maximum number of packets that can be transmitted to mobile I if it is scheduled. The channel state process is IID across slots, and we observe state M with probability pi m. And the packet arrival process is independent across users and slots. Suppose, as before, if you remember from our scheduling chapter 4, we used AI of t for the arrival process. We'll again use the same notation. A sub I of t, number of packet arrivals for mobile I in time slot t. This random variable has mean lambda I, variance sigma I squared, and the probability that AI is 0, meaning there are no arrivals, is not 0, different from 0. Okay, and there's going to be a separate queue for each user at the base station. Let's call it Q sub I of t for the Q for user I. All right, some of these assumptions can be relaxed, but for now, let's focus on these assumptions. An arrival rate vector lambda is supportable if there exists a scheduling algorithm under which Q state stays finite. This is the same definition that we used in chapter 4 for the stability of switches. So it is entirely the same definition and concept. The capacity region is defined as the following. A rate vector lambda is inside the capacity region if there exists some set of fractions alpha mi that are different from zeros, such that the ith component of the arrival rate vector is not bigger than the summation over all states of lambda mi, cmi times pi m. What is pi m? Pi m is the probability of observing state m. Cmi is the rate that user I would get if it was scheduled during state m. And alpha mi is the probability of selecting user I during state m. Okay, so this sum is like essentially an expected rate, expected service rate seen by user I, and the arrival rate of user I should be upper bounded by this. This is how we define the capacity region. Okay, now let's apply this capacity region on this example. The same example as before, downlink with two users, and the channels to the two users are on-off channels. It means they are equiprobably on or off independently of each other. So there are four possible states, right? Off, 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 on, off, and on, on. Okay, four possible states, each occurring with probability 1/4, a quarter. Right. So then, in this situation, suppose alpha 1/1 is the probability of scheduling user 1 during the state when both are on. Okay, so clearly the probability of then scheduling user 2 during state 1/1 is 1 minus alpha 1/1. Right? And you know, in the state 1/0, there is no doubt as to which user should be scheduled. Of course, user 1 will be scheduled. In state 0/1, of course, user 2 will be scheduled. So rates live inside this capacity region. Right. So let's take a look actually at this capacity region. let's skip this proof first. Actually, by the way, when you plot this region, I can just go back. We achieve exactly this pentagon that we drew before, this pentagon. Okay, so this is the capacity region. Now we'll prove that outside of this region is not achievable, meaning there is no scheduling algorithm that can support an arrival rate vector outside of this capacity region that we just defined. Okay, how do we prove it? We did a similar proof in chapter 4, if you remember. I want to go through the details of this proof because I think it is quite nice. First of all, notice that the capacity region that we defined is convex. So we can use a separation theorem. What does the separation theorem say? If there is some point outside this capacity region, lambda outside this capacity region, then there exists a vector beta such that beta I lambda I is bigger than beta I xi plus delta for any x in C. This means that the points in and outside the region C are separated strictly. Okay. So suppose that vector is positive. We found a beta vector and it's strictly all the elements are non-negative. Okay, the existence of such a beta can be shown later. So for now, let's not worry about that. And let's define a Lyapunov function, V of t, as the weighted sum of qi of t's during time t. Weighted sum of all the q's. Now, qi t plus 1 evolves as the positive part of qi of t plus the arrivals ai of t minus the departures. So we can always get rid of the positive part and use it as an upper bound, actually lower bound. Now, mu I of t is the service received by user I during time stop t, and this is equal to Cmi if the channel is in state m at time t and user I is scheduled, and it's 0 if user I is not scheduled. All right, so let's see. Vt plus 1, the value of the Lyapunov function at time t plus 1, is this, as you know, as we defined it, but by using, so basically let's write down qi t plus 1 in terms of qi of t and get rid of the positive part. Okay. Now, and then we can use recursion to write again qi of t in terms of qi of t minus 1 and so on. And we can show that this summation can be written as this summation. Okay, sum over all the all time from 1 to t, arrival at time, number of arrivals at time s, minus the number of departures at time, the amount of service at time s. When we sum this and then take the weighted sum over the users, we find the value of the Lyapunov function at time t plus 1. Then let's change the order of summations here and apply the strong law of large numbers. In the limit as time goes to infinity, 1 over t times this summation by the strong law of large numbers is equal to beta I lambda I with probability 1. Now, because of this, because of this equation here, beta I lambda I is greater or equal to beta I xi plus delta, where xi is anything inside the capacity region, with probability 1, this limit can be upper bounded by beta I, alpha mi, cmi, summed over all users, summed over all time and averaged out, plus some positive number. But again, using the law of large numbers, this fraction converges to the expectation of the service mu I of t. And from that, we conclude that the expected drift, by inserting this inside here, we conclude that the expected drift in the Lyapunov function is positive. So lambda is not supportable. Basically, and the story is, the bottom line is, if lambda is outside the capacity region, we showed through Lyapunov, the Foster-Lyapunov test, that lambda is supportable. The rest of the details, for example, why we can find a positive beta, etc., are done in the textbook. I'll skip them here. You should definitely take a look at the textbook for that. All right. So this is the max weight algorithm, and what is the essential property of max weight that makes it such a strong algorithm? It is traffic blind. It does not need to know the arrival rate vector in order to do the right thing. Remember, in our earlier, remember our two-user example, where we were able to achieve capacity through adjusting the alphas, the fractions, based on assigning the channel to user 1 if its channel is on and the other channel is also on with probability alpha I. But how do you find the alpha i's in general? You would need to know something about the arrival rates. Well, max weight does not need to know anything about the arrival rates. It is traffic blind. What does it look at? It looks at the Q states. Well, because of that, of course, its computational complexity is high, but still, it's a very powerful algorithm, and there are lots and lots of approximations of max weight that are used in practice. Now, here is the statement, the general statement for max weight. At any time, transmit to mobile I such that I is one of those indices that achieves the maximum of this expression, which is the rate that user J can achieve during the state at time t, during the channel state that is valid at time t, multiplied by the Q size of this user. Okay, so C times Q. So choose one of the users that maximizes capacity, the rate times the Q state. So if user's Q is large, but if they achieve the rate that can achieve is small, this product can still be small. On the other hand, if it is currently enjoying a good rate, but its Q is empty, again, this product will be 0. The user will not be selected. So among those users who have a high high product for rate times Q, select one of them. There may be more than one user that achieves the highest. In that case, you can break ties at random because normally the probability that this kind of situation will happen is small, so nothing it won't hurt the throughput in the long run. All right. So there is this concept, rule of thumb in queuing theory and scheduling. It's called the C-mu rule. So the C-mu rule essentially means serve the queue or the user who needs service the most, but who's able to get a high rate at the same time. It's like a rate, so here it is the rate and the queue size. The queue size shows how badly this user's queue needs service, and the C serves its potential for using the capacity of the channel. Okay. Now we can state for completeness the theorem that for any lambda inside the capacity region, the Q vector is positive recurrent under max weights. This means for any rate vector that is stabilizable, max weight stabilizes the Q. The proof is essentially the same as the proof of the optimality of max weight that we showed in chapter 4. You can read it in the textbook. So now let's consider applying max weight on our on-off downlink example. Remember that we have 4 possible channel states, 0, 0, 0, 1, 1, 0, 1, 1, with equal probabilities, 1/4 each. With max weight, what are the corresponding alpha MIs? Well, alpha M1, the probability of serving user 1 in each state is the following. 0, 0, probably 0 because it's not going to service. In 0, 1, again, user 1 will not get service because the weight of Q times C is 0. In this state, 1, 0, it will get service with probability 1. Only in this state, 1, 1 state, the probability is different from 0 or 1. User 1 will receive service during the state only if user 1's Q is larger than user 2's Q. Okay. Similarly, lambda M2 is 0, 1. Alpha M2 is 0 or 1 or 0 in the state, and in the 1, 1 state, it's 1 minus the probability that Q1 is larger than Q2. Okay, so now suppose for simplicity the arrival rates into both Qs are the same. So then by symmetry, if we keep applying max weight, it is easy to see that the probability that Q1 is larger than Q2 is going to be a half. Then the achieved rates by summation of this alpha mi, c mi, pi m are going to be 3/8 for both users, which corresponds to the following point, 3/8, 3/8. Note that max weight achieves this boundary without knowledge of the lambdas. So this point at the boundary is where the boundary of the capacitor region crosses the lambda 1 equals lambda 2 curve. When lambda 1 is not equal to lambda 2, max weight will achieve other points on this boundary. But it will always achieve the capacitor region. And it is striking that it does this not based on the arrival rates, but simply by responding to the Q state. So to finish this discussion, I want to take a quick look at exercise 5.1 from the textbook. The capacity region of a very simple cellular network scenario, consisting of a base station and two receivers, mobile 1 and mobile 2. The same scenario we've been considering throughout this lecture. Except now, the network is not on-off. The channels are not on-off. There are two channel states that are equally likely. In the first channel state, the rates achieved by user 1 and 2 are 1 and 2. And in the second state, the rates achieved are 3 and 1. Okay. Assume that the channel state process is IID across time, and the base station can transmit to only one mobile in each time slot. So we assume orthogonal transmission picking only one mobile in each time slot. Draw the capacity region. Now, let's see. In state 2, user 1 is enjoying a much higher rate, 3 times as high as the rate achieved by user 1. And in state 1, user 2 on this time enjoys a rate twice as big as the rate achieved by user 1. I'm sorry. So it makes sense for a policy to give priority to user 1 in state 2 and user 2 in state 1. Let's see if that's going to happen with max weight. So I now would like to maybe switch to the whiteboard and try to draw this capacity region. Let's see. Well, I don't have my, I do not have an opportunity to use the stylus because I'm using this computer. Let's see if I'll be able to do this. Let's see. Let's see if I can draw using this. The capacity region of lambda 1, lambda 2. Now, I will draw a region and I will ask you to think about it. And in the next lecture, we'll talk about the derivation. So what are these points? These points are 0, 1.5. And this point is 2, 0. And this point is 1.5, 1. Okay, and this is achieved with max weight. Now, it is now that I gave you this region, it is easy to in fact see how these points are achieved. 2, 0 is achieved by always scheduling user 1. Okay, when both channels are on, and 0, 1.5 is achieved by always scheduling user 2 when both channels are on. I'd like you to think about how we achieve this point. And of course, once you find these 3 points, you can always join these points. Why? Because I could always achieve anything in between through time sharing between policies. This region is convex and it happens to be the capacity region for this example. So we'll talk more about this in the next lecture.